Welcome back, everybody. We're glad to have you with us for the second day of Water Matters. We're talking about water questions today, trying to answer them or at least ask the good questions. This is part of a three-part series on water-related issues that are part of the Shout Learning online conference series. We had a great day yesterday. We had some amazing presentations. One of our presenters yesterday talked about how it's important just to look right around you and keep your eyes open. And there's a lot you can learn about animal species. And in his case, he was talking about amphibians and frogs. You don't necessarily have to travel very far. You just have to open your eyes wherever you are. This morning, we're going to start with a session which actually takes a very unique view, which is let's see how far away we can get so we can look at some of the resources that might be right next to us. We're going to look at Earth from space today, and we're going to be looking at what we can learn about global water resources when we look at our Earth from outer space, and what can orbiting satellites tell us. And we have a great guide in that in Andrew Johnston, who's the geographer at the Center for Earth and Planetary Studies at the National Air and Space Museum. We'll turn to him in just a moment, but what I wanted to do was make sure that everyone here was comfortable with how our activities here worked. So first of all, just a sketch of the day. After we hear from Andrew, we'll be turning to the Smithsonian Environmental Research Center with Thomas Jordan, and then we'll be closing out our day with two special guests from the Smithsonian's Cooper Hewitt National Design Museum, and we'll be looking at how design can address water-related issues. A really fantastic way to cap off our conference. By the way, I wanted to acknowledge and thank our partners in producing the Shout Learning online conference series. Shoutlearning.org is brought to you by the Smithsonian, Microsoft Partners in Learning, and Taking It Global. We'll be mentioning some follow-up resources with each of those partners at the end of today's session. I also wanted to mention and acknowledge as well the closed captioning that's being brought to us at the bottom of the screen by our talented friends at WGBH. And you can see that captioning appearing at the bottom. If for any reason you'd like to turn off the captioning and you don't need it or want it on your screen, there's a little pull-down menu on the right that says WGBH, and you can actually choose the menu option No Captions, and that'll turn them off. And I need to mention two more quick things. Number one, if you are following us on Twitter, please use the hashtag #ShoutLearning so you can let your friends and colleagues in the world at large know about what you're learning here during the conference, and perhaps invite them in to join us as well. It's not too late. And you can also join us on facebook.com/shoutlearning. And that's a great way to keep in touch with all of the Shout-related activities and maybe even learn a thing or two or find a neat lesson or something you can do with your classmates or your students in your classroom throughout the year. So check that out. So it gives me great pleasure to take a big step back and look back at this Earth we are all sitting on right now and find out a little bit more about the water that covers so much of this amazing planet. Andrew Johnston, thanks for being here again with us.
Thanks very much. And thanks everybody for listening in today. We're going to take the long view. We're going to look at the Earth from a great distance and see what we can find out about where water is on our planet, how it moves around on our planet, and how we can learn about those things using these kinds of tools. The view that you're looking at right now is of the Earth, of course, from a satellite used to look at weather patterns. When people think about weather, they think about clouds and wind and rain. But one thing we often forget is that when we talk about weather and even climate, we're actually talking about water moving around between the oceans and the atmosphere and the Earth's land surface. We'll look more about this kind of image in a minute, but let's take a slightly closer view. This is how we're actually used to looking at how water moves around on the surface of the Earth. As most of you are probably aware, most of the Earth's surface is covered by water. The oceans are 3/4 of the surface, and that water doesn't just sit in the oceans. It gets warmed by the sun, and it evaporates and then forms clouds. Then eventually those clouds lead to precipitation, so that water goes back to the surface of the ocean or the land surface. This forms something we call a hydrologic cycle. So I'm going to start today by talking about what that means and how water actually moves around when we look at the whole surface of the Earth. And then I'm going to give you some examples about how we use these tools based on satellites to understand how that water moves around. So here's a really quick diagram of what I mean by hydrologic cycle. Now you look at the lower right there, the area that's labeled ocean. Most of the water that we have on the surface of the Earth is here in the ocean, but it eventually will evaporate after it's warmed by the sun. And then it forms clouds, which is indicated right here. Those clouds don't sit still. Of course, clouds move. Clouds might end up some other place on the Earth. Then eventually those clouds will cool a little bit more. The water condenses out and forms precipitation, or sometimes it falls as ice and snow. Then it lands often on the Earth's land surface, where sometimes it's used by people immediately. Other times that water ends up in lakes and streams. Maybe it's trapped in geological layers, which is indicated over here on the left. Then that water flows downstream, which you can see in here. And eventually, often, it'll end up back in the ocean. It forms this cycle that constantly runs. It actually never ends. So where is the water in our entire Earth? Again, we're taking the broad view. We're looking at the entire planet all at once. Well, as you can see in this quick little diagram, more than 97% of the water we have on our planet is in the oceans. Only about 3% is in groundwater and ice caps and glaciers, as we can see right there. But if you look at this middle column here, this little tiny sliver of a percent, 0.014%, is available on the Earth's land surface, either in the form of soil moisture or lakes. And then this amount right here is what exists in the atmosphere. So when we talk about water resources that people actually use for drinking water and for agriculture, things like that, it's a very tiny percentage of the water that actually exists anywhere at any given time on the Earth. Now, don't be too worried about the details of this diagram. I just put it up there to talk about how we try to understand the Earth as a system. One of the things that we do in Earth science these days is we try to understand how the different cycles that operate on the Earth's land surface work together. So we have a water cycle, we also have an oxygen cycle and a carbon cycle, things like that. When we look at the water, I'm going to walk you through 4 different places where we actually see water on the Earth. I'm going to start by talking about water in the oceans, where water actually transports, it moves around, it heat. I'm going to talk about water in the atmosphere, so we're going to talk about clouds and rain and precipitation. Briefly have to mention solid water ice, because that actually is a lot of water that exists on the Earth's land surface in the form of glaciers or ice cover on the Earth's Arctic and Antarctic regions. Then I'm going to finish looking at a few different views of water on the land, which is actually how most of us interact with water, obviously. It's water that we can use to either go swimming or go fishing, or we can drink it, and we use it to grow crops. Well, this is an example of the kind of tools I'm going to be talking about in the next few minutes. In my job, I actually use these kinds of tools to actually understand land cover change on the Earth's land surface. So this is a variety of different satellites that are in Earth orbit right now. I don't really need to go through all the details, but I do want to mention that a lot of the images that you'll be seeing come from large satellites like these 2 right here. This one that I clicked on first is called Terra. This one is called Aqua. These are 2 satellites that return data that's useful for observing environmental processes. In fact, Aqua, as you can probably guess from the name, was intentionally designed to look at changes happening in the hydrologic cycle, how things actually move around in that water cycle that we have here on the Earth. Now, I briefly need to mention a little bit about how these tools work before I start showing you some of the data we have from them. We got to mention the electromagnetic spectrum up here. There are different wavelengths of light that exist. With our eyes, we actually detect visible wavelengths of light, which is this part of the spectrum. But a lot of the images I'm about to show you that come from Earth orbit also use infrared wavelengths of light, which are this part of the spectrum. And then a couple of the images actually use radar, which is out in this part of the spectrum here. There are many other wavelengths of light that we don't use for these kinds of tools, like X-rays, for instance, and most ultraviolet light, because that actually cannot penetrate through our atmosphere. The way these tools work is they actually look down at the surface of the Earth and the oceans, and you can think of them as giant digital cameras, kind of like the digital camera you might be carrying right now. Now, these boxes right here, don't worry about what is going on inside the boxes, but they indicate different numbers. All this data is radioed back down to the surface of the Earth as numbers. The numbers represent brightness values. So what we do is we assign brightness values to all those numbers, and we actually look at many different wavelengths at once. The sensors actually look at different wavelengths simultaneously. Then using computer programs, we assign colors to those different wavelengths of light, and that gives us a full color image, which is what you see right here. So all the images you're about to see are made using this exact same process. As the data comes back down from the satellites, it's not immediately useful. There are people that actually process the data so that we can actually understand how things are changing with the Earth's water.
And quick question, Andrew, the reason for doing that, is that make it is it a more efficient system to send things down as numbers versus full-fledged images, or is it a security concern?
No, it's not a security concern, and it's not an efficiency concern. It's actually the only way to do it. Before we had the technology to make digital images, there were actually a few satellites that were launched that used film, actual film that was exposed up in space, and then it was rolled up and then returned to the Earth in a small re-entry capsule. Those were reconnaissance programs designed to collect military intelligence. But by the time the early 1970s came around, we had this digital technology. So ever since really the early 70s, the first Landsat satellite was launched in 1972. That was a satellite operated by U.S. government agencies to look at land cover change. And that actually used digital sensors. There was also an analog sensor that was very similar to a television camera, but very early on when we had this technology, we could tell that with the digital technology, it was easier to discriminate differences on the surface of the Earth. Now, those of you that have digital cameras at home realize that we haven't had digital cameras since the 1970s, but the technology was used on satellites before it became available in commercial electronics.
Great, thank you. And by the way, if you have questions for Andrew, additional questions as we go along, go ahead and drop them in the box on the left-hand screen. We'll address them throughout the session.
I will stand by for those questions. Look forward to them. What you're looking at here are two images of the entire Earth, but you can tell they don't look like the globes that you're used to seeing. The colors in these two images indicate different things about the Earth's water cycle. The top image actually shows their land areas have been grayed out in that top image, so it only looks at the oceans. And the different colors indicate the temperature of the ocean water at the very surface. One of the very common things we do with satellites is we measure the temperature of the water that's in the oceans. Now, we don't do that to understand if it's going to be pleasant to go swimming in the oceans. We do that to actually understand how much energy is being stored by those ocean waters. That's very important for understanding how water moves around between the atmosphere and the surface of the oceans. It's important for understanding how energy moves around. So that's one of the things that we do very commonly with satellites. The lower image on the screen right now actually shows cloud cover fraction. In other words, what that means is that the brighter the area is on that lower image there, the more clouds that we have over a period of about 1 month. So in other words, if you look where the pointer is right now, this indicates that that part of the North Atlantic has had a lot of clouds in this particular month, whereas this area where I'm pointing right now has had almost no clouds. Now this tells us about how the Earth operates. Where the pointer is right now, if those of you that know your geography are aware that I'm pointing at the Sahara Desert, which is an area that has very little water on the surface, which is going to mean we're going to have very few clouds. Whereas where I pointed out earlier is actually a part of the Atlantic Ocean that we have something called the Gulf Stream, which is a stream of relatively warm water flowing from south to north towards the North Atlantic. With that warm ocean water, that will tend to produce a lot of cloud cover and then a lot of precipitation. So we use these kinds of images to see how the entire planet works as a system, and there are interlocking systems within that. This image actually shows atmospheric aerosols. So it actually shows how much microscopic particles are floating around in the Earth's atmosphere. I'll mention this again in just a minute. There are some important interactions between how much aerosols are floating in the air and how much precipitation we can expect to have. Well, here are two views of the Earth that are probably a little bit more familiar. They look a little bit more like globes. But again, they highlight different parts of the Earth's hydrologic cycle, or the water cycle. On the left is a snapshot of cloud cover. So this is an image returned by satellites that shows where clouds exist on a particular day. So we're focused on the Indian Ocean there. Australia's on the lower right there, and then Africa is over here. And the bright areas show cloud cover that's visible from space. On the right, what we see is an image of atmospheric water vapor. So the brighter parts of the image on the right indicate that there's more water vapor in the air. So what we see are these gray areas. Now these gray areas don't mean clouds. In other words, if we were right here in a boat, we would look up and not see clouds. In this case, the gray indicates that there's a lot of water vapor floating around in the air. But down here, near the Earth's equator, we have this band of very high water vapor where there probably are some clouds. Now keep that band in mind, because we're going to show you another image in just a minute of what that band of clouds actually looks like up close. Two more views. Now we're looking at the Earth's oceans. On the left is a global view of the Pacific Ocean, color-coded by temperature. So this is another view of the surface water temperature. So the reds show high temperatures and the blues show relatively cold temperatures. But measuring the temperature of the water by itself is not usually what we want to do to understand the Earth as a system. We want to do, what we would rather do is look at changes or where things are unusual. So on the right is an image of the Earth's oceans. This is the more eastern part of the Pacific Ocean now. But this shows what we call sea surface temperature anomaly. In other words, these are areas that are cooler or hotter than average. So the bright reds show areas where it's significantly warmer than it would usually be at the time of year this image was collected. And in this case, you can see that we have a large area of red here, which indicates not that these waters are particularly hot, but it means that they are hotter than average. This is a process that you're looking at here that we call El Nino. It's an oscillation of warm water that fluctuates back and forth across the Pacific Ocean. And when those warm waters fluctuate over here towards the coast of South America, it will change the productivity of the waters. In fact, it was fishermen in Peru that first noticed this phenomenon, where they noticed that they were catching fewer fish when this would happen. And when it first happened, we didn't understand exactly how the process worked. But now, using satellite data, we can follow that blob of warm water back and forth across the Pacific Ocean so that we know it's this oscillation that happens as a process that happens over a period of 10, 15 years.
And presumably with that data and those trends in mind, are there people on the ground doing things differently or making preparations as a result? Is it used in some kind of predictive way?
In this particular case, no. We have learned a lot about how we now call it the El Nino Southern Oscillation. We know how that process works, but we do not have very much predictive power in this particular case. We cannot predict that, for instance, next year there will be an El Nino. The opposite of an El Nino is called La Nina. It's the nickname for it. So it's not something that we can predict with any precision over the next 2 or 3 years whether or not, for instance, fishermen in Peru will be seeing their catches drop. We are still learning about that. The only tools that we have that will really enable us to understand those kinds of processes better are the satellites that give us the images that we see here. So let's talk about water in the oceans, that first part of the water cycle that I mentioned, because obviously that's where most of the Earth's water is. And here's another image of sea surface temperature. So this is a global view. One of the things that you can see, the red colors show the brighter, they show the warmer waters. In this case, the warmest part of the Pacific Ocean is not off the coast of South America, so we're not looking at a picture of an El Nino period. But over here, the warmer waters are over here closer to Indonesia and Papua New Guinea. Well, let's take a closer look at some specifics about the ocean temperatures. I'm going to be showing you a lot of very attractive images in the next few minutes But I had to start by showing you some unattractive images because honestly, most of the time when scientists use these pictures, they look more like what you're looking at on the screen right here. So remember I explained sea surface temperature anomaly before. This is a map of that sea surface temperature anomaly. So you see the scale across the bottom here. If something is blue or dark blue, that means that the water is cooler than average than it would be expected this time of year. If it's yellow, it means it's pretty typical temperature. If it's red, that means that the temperature is higher than it would be expected. So you can see we've got a lot of yellows and light blues. So over most of this image, the temperature is about what we would expect, but there's a few examples of something else going on. Here's some warmer than average temperatures. This is, again, that thing that I mentioned before, the Gulf Stream. I've got another image of that coming up in just a second. And then some areas maybe in the Gulf of California here that looks like it's cooler than average. Yes, and it does look like old 8-bit video games, the kind of video games that I played when I was a kid, but I might be older than a lot of people watching. But it does look like those old video games because this is a very simple image. This is you can see all of the steps there. Those are individual pixels or picture elements that give you an idea of the kind of detail that we can see. Some of the other images I'll be showing you show a lot more detail, and I'll explain in a minute actually how that's done. So remember I mentioned the Gulf Stream. Well, here's one of those more detailed images that shows an image of the Gulf Stream. Let me orient you first of all. This is the coast of North America right here. This is the Outer Banks of North Carolina right there. This is cloud cover. All this white stuff that you see is cloud cover. Although up here, very far north, this is now up into Canada, this white area is actually snow cover on the ground. Out here in the ocean, this is the Atlantic Ocean. We have lots of cloud cover. But you look here, this is the surface of the water. Now, the surface of the water is not actually this color. Obviously, those of you that have been to the ocean know that the ocean waters are not bright blue or orange or red. What's going on here is that these colors indicate different densities of chlorophyll. Now, chlorophyll is the pigment that's present in the leaves of plants, but it's also present in microscopic organisms in the ocean called phytoplankton. Now, these little tiny organisms are the base of the ocean food chain. So what they do is they use sunlight to grow and build their bodies, and then other creatures like fish eat those phytoplankton and grow themselves. We actually can build satellite sensors to detect the presence of chlorophyll. So in this area, what we're seeing is higher and lower densities of chlorophyll, which indicates where lots of microscopic organisms are growing. Now, it turns out that the amount of nutrients that are present in the ocean waters is actually tied towards their temperature. So if we have cooler temperatures, we sometimes actually have higher levels of nutrients because they can be chemically contained in that water better than warmer water. So we've got this area here. This is this area called the Gulf Stream, where we actually have slightly warmer temperatures, and then we have slightly cooler temperatures right here, so we have more organisms actually living in that part of the ocean where the pointer is pointing. Now, sometimes these flows that happen through the ocean can branch off little spirals called gyres, and that's what that thing is right there, if you see that area. That's a little spiral that exists in the ocean. If you were sitting there in the boat, you would not see any difference in the color of the water. But we can detect the difference in the amount of chlorophyll from space. Now, these kinds of images are useful for understanding how large-scale biological changes can happen over the Earth's ocean. And because we're directly detecting the presence of those microscopic organisms, we can't directly detect the presence of things like fish and whales, for instance, from orbit, but we can detect where those larger creatures would likely to be living because they want to eat the little microscopic organisms. So that's a brief look at the water in the oceans. Now let's look at water in the atmospheres.
There was a question a little while ago
Sure.
when we were talking about El Nino and La Nina. Do we know if those oscillations that we can detect are affecting storm cycles, was the question that came in.
Really good question, and the answer is absolutely yes. There is a big impact between that El Nino southern oscillation and precipitation patterns in many different parts of the world. It impacts precipitation that happens in Australia and also in North America. You can expect either wet years or dry years depending on where that oscillation is. I should mention that in most years, that oscillation is not completely at one end of the spectrum or the other. At most years, it's in between. But when we have very warm water that exists either close to Indonesia or close to South America, that's going to change precipitation precipitation that we expect to see on both ends of the Pacific Ocean. Yeah, and in fact, sometimes it affects the weather predicting that happens in places like South America, but even the southwestern United States, where we would expect to see maybe more precipitation or less in places that are traditionally dry because it's an El Nino year. Yeah.
Great, thank you.
So you're looking at an image now from a sensor called CWIFS. This sensor no longer operates, but it was in Earth orbit for many years, and it actually shows a tropical storm in the center there over the Atlantic Ocean. Again, just to show you the geography, there's Hispaniola, this is Cuba, there's Florida right there. So we're looking from west to east, and of course that curve is the limb, that's the edge of the Earth. So we can actually see water moving around in the atmosphere, and one of the ways we often see that is cloud cover and large storm systems. Here's a view from one of these satellites that is used to look at weather patterns. So we are looking at the extent of North America. So here's the west coast of North America and the east coast. This is Mexico right here. And these bright white areas are tropical storms. Here's one, and there's another one. So this particular picture was taken when we have hurricanes actually moving towards North America. These large tropical storms form because water near the Earth's equator in the oceans is warmed, and then that water evaporates, and warm air with lots of water vapor rises in the atmosphere. It eventually cools as it gets very high in the atmosphere, and then forms cloud cover. Well, that moving air also starts to generate energy of its own, and eventually forms these large storm systems that usually just move around in the ocean, but sometimes they move towards land masses. And when that happens, those large storms actually transport huge amounts of heat and water vapor from the Earth's equator to areas that are more further away from the equator in northern latitudes. Here's a really nice image of a typhoon called Hygos in the Pacific Ocean. This storm actually impacted Japan. I should mention that typhoons and hurricanes are the exact same thing. It's just in the Americas we call them hurricanes, but they're typhoons if they're in the Pacific there, and in the South Hemisphere, and also in the Indian Ocean.
Andrew, there's a question about the scale of this photo.
Really good question, and thank you for reminding me. I will try to mention that every time I show you these images. The particular image you're looking at right here, is probably a good 180 kilometers across, or about 120, 110 miles. So it's a really large storm. This particular storm, Hygos, was the largest storm to make landfall in Japan in many, many decades. And so this is an image from the MODIS sensor on board the Terra satellite. It wasn't necessarily designed to show us images of weather patterns, but it just happened to return this image. And you can see the swirling clouds around the outside, and then in the center is the eye of the storm. And then as long as this storm exists over warm water, it's going to continually being fed energy from that warm water. Eventually, though, these storms move to higher latitudes, so they move away from the Earth's equator, and they go over cooler water or the land surface, and they run out of energy, and eventually they always dissipate.
I'm sorry, this is a personal question from my own techie background or interest. You mentioned that this particular satellite just happened to pick this image up. It's not necessarily a weather satellite. Are there ground triggering systems that are automatically pointing cameras in locations where humidity is detected or changes, ground detections are happening, or is this always human operators deciding where to point these things?
It depends. Let me go back to show you this view. This view is from a satellite in a very distant orbit, and and it returns images very frequently. We get an image from this kind of satellite about once an hour. And this kind of satellite looks at the entire hemisphere of the Earth. Remember the picture I started with, back about 30 minutes ago. This kind of satellite just returns images constantly, all day long, sometimes all night long. So there's no human intervention because we want to know where those storm systems happen. This kind of image that I just showed you returns images not constantly, but usually when it's over the Earth's land surface. This particular sensor is designed to look at land surface interactions between the atmosphere and the oceans, but it doesn't return constantly. It is in a lower orbit. You're looking at the entire what we call field of view of this satellite, so it doesn't look at the whole Earth all at once. It just looks at a tiny portion. So what we do is we can take these smaller images and place them together to look at large areas, but it works slightly differently. There's another class of satellites that actually looks at very small details, and those kinds of satellites are operated by humans that actually make decisions about where I want to look at this satellite or this part of the Earth's land surface or that part of the land surface. So it all depends what you want your satellite to do. If you're looking at weather patterns, you want the satellite to just be looking at the whole Earth and constantly return images. If you want to look at this kind of scale or this kind of area that you're looking at the screen now, it returns images most of the time, but not all the time. But if you're looking at very fine details, because you can't look at the whole Earth in very fine detail, you want to have human operators deciding when it's sending back images.
Great. Oh, I'm sorry, one more question from Clea. How many weather satellites is NASA using right now?
NASA actually does not operate weather satellites. The weather satellites operated by the United States, for instance, are run by a different government agency called the National Oceanographic and Atmospheric Administration, or NOAA, N-O-A-A. That government agency actually has 2 satellites that are in orbit right now in what we call a geostationary orbit. So it goes around the Earth once every 24 hours. So it maintains a constant view on one half of the Earth's surface. There's one satellite that sits over the Atlantic coast and one satellite that's over the Pacific coast. And then there's a spare that's in orbit in case one of them breaks down. There's also a European consortium of nations that operates weather satellites. They operate a weather satellite over the European coast of the Atlantic Ocean, and then another satellite over the Indian Ocean. And then there's a Japanese weather satellite agency that operates constantly a satellite over the western part of the Pacific Ocean. And then there's also weather satellites operated by other nations, such as Russia.
So not hobbyists.
No.
We can't get into this ourselves.
No, these kinds of satellites cost hundreds of millions of dollars to build and launch and operate. Weather satellites the governments of the world have made a decision that the satellites that track weather patterns are a very important thing to do. So they actually have agreed to divide up which satellites observe which part of the Earth. And so a lot of resources go into that. Some of the other satellites that I'm going to show you are operated very differently. Most of them are operated by government agencies, but not all. So to give Clea a final answer, the U.S. government always operates 2 weather satellites in that geostationary orbit, and other nations operate many more.
Excellent. Thank you, Clea.
Sure. So let's move on here because we're already more than halfway over. Remember, I told you to keep in mind that band of clouds around the Earth's equator. Well, here's an image that actually shows that very clearly. So this area right here is a band of clouds. This is what we call the intertropical convergence zone. So this is a part of the Earth's land surface that gets more sunlight than the rest of the Earth because the Earth's equator has more direct sunlight, so it tends to get more heat. So the water of the ocean gets more it rises in temperature more than the surrounding areas. And remember, I explained before how that can create cloud cover. So that's why we have this convergence zone right here where air at lower levels of the atmosphere is right here where my pointer is, but it flows in, it gets heated here, then rises and forms clouds. So this is that convergence zone around the Earth's equator. Now this band of clouds fluctuates with the seasons. So when it's summer in the northern hemisphere, this band of clouds will be a little bit more north. When it's the summer in the southern hemisphere, it'll fluctuate down here. But there's a lot more precipitation in this part of the Earth than there is north and south of the equator, which is why we have tropical forests in places like South America right here. and tropical forests elsewhere around the Earth's equator. Here's an image, again, from that MODIS sensor on the Terra spacecraft that shows flowing clouds. These are the Canary Islands. There's the coast of Africa there in the lower right. And these islands actually present a barrier for the movement of clouds. So the wind is blowing from north to south. This is an image that, again, is close to something like 200 kilometers across. So we're looking at a large area. But the wind is moving in this direction, blowing those clouds, and it's not quite getting around these high hills on the Canary Islands right there. This is an image looking at hundreds of kilometers across, and this is what we call an oblique image. What that means is we are not looking straight down. So if you look at the top edge, you can see this curved line here. This is the edge of the Earth, and there's the Earth atmosphere. We are looking at the Great Lakes in North America. So this is Lake Michigan right here. The city of Chicago is right there. This is Lake Superior. What's going on here is that it's a pretty clear day, but the air is moving out of the northwest and moving in this direction. What happens is that the Earth is blowing over the Great Lakes, these bodies of water here, and it's picking up water moisture from the lakes. And then that water forms clouds, and then it causes precipitation downwind from the lakes. In fact, the city of Kalamazoo, Michigan, which is right here, 11 inches of snow fell in Kalamazoo on the day that this image was collected. This is what people in that area call the lake effect snow. So water vapor is picked up, it moves from the lakes, the water moves into the atmosphere, and then falls as precipitation downwind.
Yep, we have a comment here from one of our participants who's from the Canary Islands and didn't have any idea that they played such a role in the weather. So thank you,
let me just go back to that briefly. This part of the image right here is what we call a vortex street. So you see all these swirling patterns. That happens because one of the islands interrupts the flow of air a little bit, and so forms this string of swirling vortices downwind. It's a really neat.
It's an amazing image.
Let me move. Now here's an image that actually needs a little bit of explaining because you see the dark lines there. Those lines do not really appear in the real world. Now these are political borders that have been added after the fact. So here's the border between U.S. and Canada, for instance. New York City is right there. Now this bright area is cloud cover over Labrador here and then also over the Atlantic Ocean. But you see this area here that is a slightly different color? That's actually not cloud cover. It's not water vapor. That's actually smoke from forest fires that have been burning here in Quebec. So what happens is that in this part of Quebec there were forest fires, so that smoke rose in the air, and it happened to be a wind blowing from north to south and blew all that smoke. Then you can see right at the edge here, this is how far the wind had blown, blowing those clouds out of the way. The smoke didn't cause the wind, it just happened to be there at the time. So this part of the northeastern U.S. actually had very smoky skies temporarily. One of the things we've learned using these satellite data is we've seen how clouds can move around, but also how things like dust and smoke can move around in the Earth's atmosphere. Briefly wanted to show this picture because this is a color-coded image showing actually the size of water droplets that are actually in water vapor in the air. I mentioned before that these microscopic particles that we call aerosols, there's a connection between that and the kind of rain and how much rain we will tend to get in the clouds that form in those areas. Again, this is not the most attractive image, but it's an important image for scientists for understanding these global scale processes. Now I want to talk a little bit about water in its solid form, because there is a lot of ice on the Earth's land surface. What you're looking at is a picture of a part of what we call the Lambert Glacier, which is actually in Antarctica. This particular image is probably 40, 50 miles on a side, that kind of size, and it's entirely ice. But the ridges that you see are caused by flowing ice. The ice actually moves slowly from this area, then it flows down a ridge here, and eventually moves out over the ocean surface. Ice, we're used to ice being a solid thing, but it actually does move slowly on the Earth's land surface. This is an image of the entire continent of Antarctica. This is Antarctica as it appears in a radar sensor. All of the images that I've shown you so far are from reflected sunlight. So another light comes from the sun and is reflected off the Earth, and we detect it in orbit. This image is different in that the satellite actually produces its own pulse of energy that then reflects off the surface of the Earth. So we can see through clouds. We can also see the details of ice cover. So this is the entire continent, and the ridges that you see here are details in the surface of that ice. One of the things we do with satellites is we detect changes in the ice. Is the ice getting thicker or is it thinner? And how fast is it changing? Here's an image from the Landsat 7 satellite of the Malaspina Glacier, which is in Alaska. This image is another one that's probably a good 40, 50 miles across. So that's 60, 70, 80 kilometers, something in that neighborhood. And the different colors actually show different kinds of land cover. So this glacier actually forms at the upper edge of this image. So snow falls over here, and over many years the snow gets packed down and forms layers of ice. Slowly but surely that ice flows downhill and then forms this area right here, and then the ice melts as it gets down here, and this is the coast of this is the ocean down here. Now, these colors are not real. The dark reds here indicate the presence of vegetation. Remember I mentioned before we're looking at different wavelengths of light. In this case, the red indicates reflectance in near-infrared light, which tells us there's plants growing there. But see all these lines here? These are different layers in the ice that are actually visible as the ice melts. Every glacier that exists on a mountaintop gets bigger at the top of the mountain, and then it flows downhill, and it melts at the bottom. One of the things we're interested in doing is seeing how glaciers change through time. Glaciers in this part of Alaska and in most of the world are on average slowly getting smaller because they're melting faster at the bottom as the ice is forming on the top. That's one of the indications that we have of a slowly warming average temperatures over the Earth's land surface, at least at a global scale.
Andrew, it's amazing in how many of your images we are using some sort of proxy, some sort of replacement for understanding what is going on the ground, from the plankton and the algae growth in the oceans to looking at the melting of glaciers by studying something other than the ice.
Right. The goal for what we call Earth system science, for understanding the Earth as a whole, is to understand these very large-scale patterns and how they change through time. And then we can understand how those large-scale patterns impact things that happen at a local scale, which is the local scale is what usually matters to people in their everyday life. So whether or not you live on a particular glacier or not, it might matter to you if you're trying to go skiing on that particular mountain or something. But if you don't live there, it might also be interesting because it can help you understand these global scale patterns to see how it can impact what does happen in your local environment.
And I see a couple more questions. We will return to them momentarily, but I'll just mention one of them right now in case you can weave it in as we look at some additional images. Aliha in Pakistan is curious if you have any information on Asian weather as well.
In fact, I've got a series of images coming up in just a few minutes that talks about water flowing on the surface through places like Pakistan and India. So remind me if I don't get to it, but I will get to that in just a minute.
Great.
So let's move to talking about water on the land. The land is obviously where we tend to live. So this is the kind of water that maybe matters more to a lot of people. We have images that show actually how water is actually measurable from the Earth's orbit, and also how it actually impacts how it looks on the surface. You're looking at a really crazy image of the Florida Everglades. This is in the southern part of Florida. The different colors here are not real, again. They actually show different kinds of vegetation. In this part of Florida, what happens is that the water moves from north to south, so from the upper part of this image to the lower part, and the different kinds of colors that you see there indicate different types of vegetation that's growing that takes advantage of that. This image is probably about 100 miles from left to right in size. This is another image that actually shows how we use water resources on the Earth's surface. This is in the central part of the United States in Kansas. The circles that you see there have been created by farming. Agriculture was actually happening there, and so that's a process we call center pivot irrigation, which is a very efficient form of irrigation, where we actually pump water from wells up to the Earth's surface to make crops grow. The red circles indicate where crops are actively growing. Again, that red shows vegetation. The white circles are areas where either the crops are not growing or they've already been harvested. Again, this is an image that's maybe 50 miles across, more like 70 kilometers across. So what's interesting to note is that the red circles that you see are mostly on the northern part of this image, which happens to be near where the Arkansas River flows. So it might be possible that there's a slightly easier to get water table in this area, so we have slightly more irrigation going on there.
Elizabeth from Ellicott City, Maryland, says it's a little off topic, but it just came to her right now. Do man-made lakes, ponds, etc., throw off the natural balance of the environment around them, or can they be a positive factor?
It's probably better to say that things like lakes and ponds and dams alter the pre-existing balance of how water flows over the surface. Whether they're positive or negative really depends on who you are and what you want to do. If you live in a very arid area where it doesn't rain very much and you want to be able to grow crops or just drink water, you might be very happy that there's a dam there, ponding that water. But if you happen to live downstream, you might not be very happy because now you don't get as much water as you might have otherwise. But it is definitely true to say that the way that water flows over the surface has been significantly altered by human-built structures. There's absolutely no doubt about that. The image that you're looking at right here is actually color-coded based on data from another one of these radar satellites. This actually indicates soil moisture. So the blues show where there's a lot of soil moisture in the southern part of Africa, and the yellows to reds indicate where there's not much soil moisture. These tools are still under development, but we're learning more how to actually measure soil moisture from Earth orbit over large areas to see where the resources are healthy, or maybe where it might be slightly more challenging. And I will talk about wetlands in just a second. Here's another area where humans have drastically altered the Earth's land surface. This is in Egypt. You're looking at the city of Cairo. The gray area is the urbanized area of Cairo. Millions and millions of people live here. And this is on either side of the Nile River. I should mention, here's the Nile River right there, which is, of course, flowed for many thousands of years, and an ancient civilization there. And there's the modern civilization. On either side of the Nile River, it is an arid desert where it almost never rains. But what they've done is people have diverted water from the Nile for irrigation. So the bright reds that you see out here are irrigated croplands. And we can detect that from orbit, as you can see. So this is a very common to see this kind of alteration of the Earth's land surface, where actually we can change how water is flowing and use it for human uses. Now let me try to finish up as fast as possible here, because we're running out of time, talking about water on the land as it's flowing over the surface. Here's an example of one of those finely detailed images that shows water flowing over the surface. This is Victoria Falls on the border between Zambia and Zimbabwe. On the lower right there, you actually see a hotel for tourists, but this is just an image that's sometimes useful for looking at very fine details of how water flows over the surface. This is the city of Detroit, and the Detroit River in the center there is connection between the two Great Lakes. The different colors here are not colors of the water, but they actually show what we call the amount of turbidity in the water, or in other words, how much microscopic particles are actually floating in the water. Here's a before and after image showing flooding in Dongting Lake, which is in China. This actually shows two images of the exact same part of the Earth's surface, but we're actually showing it before and after flooding. Actually, I should say during flooding. This is a natural process, and there's overflow from a river where it floods the Earth's land surface, and then here slightly cloudy conditions after the flooding is over. We very often use these kinds of images to see areas that have flooded and where areas have not. Here's an image of, talking about flooding, of an area around Banda Aceh, Indonesia, which was one of the hardest hit areas after the tsunami that happened there a couple years ago. Same exact part of the ground, but here's the city right here before the tsunami and after. So this isn't really an image of land surface water flow. This is ocean flow, but it does indicate how we can actually make maps of areas affected by disasters, which we often do when we talk about the impact of water flowing over the surface. Well, now I'm going to take you to Central Asia. This is actually an image of mountains in Bhutan that actually shows glaciers very high in the mountains. This is part of the Himalayan mountains. So this image is a good 40, 50 miles across. I'm sorry, 40, 50 kilometers across. This is a slightly smaller area. So here's the ridge of mountains in Bhutan. And then you can see these glaciers flowing down. They're made of solid ice, but it's flowing down. As I said, all glaciers eventually melt. When they do, they melt and form rivers. So this is the braided channels of the Brahmaputra River. In this particular case, we're looking in northeastern India. So that same water that you saw in the glaciers just a second ago melts and forms this river as it flows downstream. And then eventually the Brahmaputra River, which is right here, joins the Ganges River right here. So we're now in India and near Bangladesh, and that water continues to flow downstream and eventually emerges out into the Indian Ocean, which is what you see right here. So we've just followed the course of one of the world's great rivers. It starts in the mountaintops with frozen ice, and it melts and then flows out into the ocean right here. This color here indicates there's a lot of sediment floating in the water. This dark green area here is an area of wetlands. I see that we've got a lot of questions and comments about wetlands right here. In fact, I got another image of the same area. This was taken from a handheld camera by an astronaut in space. In this case, we're looking at the entire area of wetlands that I just mentioned before, but now we're seeing the sun glint off the water here, and all this area here where you have low-lying areas that are saturated in water that actually has a particular kind of vegetation that grows there, and there are important connections between that and local climate and even global climate. If it's okay, I'll try to press ahead and finish up because I know
we'd love to see these images.
Okay,
we're good.
great.
And remember, if those of you need to log off, we're recording it. You can catch the last few minutes, but keep going. Ed.
So what I'll do is I'll try to finish up and then I'll stick around and we'll take questions. Maybe we'll just press ahead and finish here.
Yeah, you got it.
Okay, so we just followed the Brahmaputra and Ganges rivers from its mountaintop sources to the ocean. Let's quickly do the same thing with the largest river in the world. This is the Amazon River. So on the left here, you see an image from a Landsat satellite that shows an area maybe 60, 70 kilometers across. The most distant sources of the Amazon River are located right here in the tops of these mountains. Now, the picture on the right shows this mountain where the cursor is right now, but this picture was taken from an aircraft, of course. And you can see up here, here's the snow and the ice at the very top of the mountains. And then this snow melts and forms streams that flow this way. So this is the Amazon drainage basin. When most people think about the Amazon, they think about jungles, but it's very dry and very, very high altitude here. If you follow the Amazon River right here, this is in Brazil. This is called the Rio Solimões, and it joins the Rio Negro right here, flowing out of Venezuela at the city of Manaus. You can see that the two rivers have very different colors because the Solimões has a lot of sediment in it, whereas the Rio Negro does not. And then when they join here, and it's called the Amazon from here to the ocean, the waters don't join. You see, they still mix. They don't mix until you get further downstream. But then eventually they do mix, and then it flows across Brazil and enters the Atlantic Ocean. And all that sediment that you see is what you see right here, flowing out into the Atlantic Ocean, which is the upper right part of this image. And here's the delta of the Mississippi River in North America, the largest river in North America. And all that sediment that is eroded, I should explain, that's eroded rock that's carried in the water. All that sediment is deposited out here in the Gulf of Mexico and forms these bars of land. So the water continues to flow out into the Gulf of Mexico and forms that distinctive pattern. And here's the same kind of thing, but this is the delta of the Mekong River in southern Vietnam. And you can see the sun glint that's visible through rice cultivation right there. And then I'll just finish up with a very brief view looking back, way back in time. So what you're looking at is an image from a sensor looking at the western desert of Egypt. There's not very much water here. This is the color as it would appear to your eyes. So it's all covered by sand, except we have a ridge line right here. There's a line of hills right there. But we can actually use that different kind of sensor to look through the Earth's land surface and to look just beneath the surface. So this is using a radar sensor in this area strip of data in the center. If I cover the whole area with the radar data, it looks like this. So instead of the sandy surface, you see these patterns right here. It looks kind of like river channels. In fact, that's what these are. These are ancient drainage channels. There used to be streams that flowed downstream. And in fact, now there's a desert oasis located right here. When we go out into this part of the world, we often see features that look like this. This is a photograph taken from the space shuttle. Covers an area about 10 miles from left to right. That's an ancient drainage channel. That used to be a stream. Nowadays, it never rains there. It almost never rains there. But we know it used to be a stream because we see the evidence. We see the erosion. We also see evidence of human habitation. We see the presence of animals that used to exist back then. So if you go back in time 20, 30,000 years, this part of the world had rainfall and streams. But then the climate changed, and now we have an area that's mostly dry. So one of the things we try to do is we look at current changes in the Earth's atmosphere, but we also look at the geology and we look at the Earth's surface to try to understand ancient changes to see how the Earth and maybe even other planets might change through time. So I'm just finishing with that same image that we started with there. It's a good view of North and South America, but also shows the water cycling around in the atmosphere. That's a really quick tour of the entire Earth as we know it from the perspective of water and how water moves around. Thanks very much, and I'm happy to take any more questions.
Andrew, thank you very much. What an amazing vantage point, and what a cool job you have to be able to not only look at images, but to be able to bring some meaning to what it means to us on the ground and how we take care of our planet. And I want to thank everyone also for their great questions that you've added throughout the session today. Fantastic. Do note that what we'll be doing is taking a 1-hour break, and we will be returning with a session on the nitrogen problem, causes and remedies, and we'll be turning to experts from the Smithsonian Environmental Research Center, including Thomas Jordan, who's a senior scientist there. So we hope you'll stay logged in and join us for that session. We're happy to sneak in an additional question or two. I did want to just very briefly mention that we have some additional resources for you. Don't forget to join us on our Facebook page, which is facebook.com/shoutlearning, where we'll continue to provide resources, updates, news about upcoming conferences and events. And we'd love to see you on there, so go ahead and like us on that site. I also wanted to point out a couple of other important resources. Don't forget as well, yesterday we launched the Smithsonian Shout Learning Quests, and you can check those out online. I'll give you the link in just a moment, but this is a great place to continue your investigation on these topics and even have something to show for it to help others know that you have become an explorer about the land and the water, which are the two themes we've covered so far in the Shout program. So that's the Smithsonian Badging Program, and you can sign up for it for your classroom. You can check that out. That's at smithsonianconference.org/shout, where you entered the event /badges, and sign up, and we'll just let you know how you and your classroom can get involved in the badging project. Also wanted to just bring up a couple of other things. Don't forget here that you can join, if you're a teacher, we encourage you to join the Microsoft Partners in Learning Network, which is a network of educators from around the world. And you can also find the technology tutorials available through Taking It Global and Microsoft Partners in Learning. So you can see a link on that screen. You can also find this link directly at shoutlearning.org, and we encourage you to check out those technology tutorials, a great way to learn how to better use technology in teaching and learning about the kinds of things we're talking about today. So we're going to go ahead and give you a little bit of a break. We hope you'll enjoy it. Stay logged in, stay connected, and we'll be back in 1 hour for our next session from the Smithsonian Environmental Research Center. Thanks, everybody. Thank you again, Andrew.